Welcome. On this day 70 years ago, Einstein passed away. To honor his legacy, I present his general theory of relativity, from its foundational principles to its profound predictions about black holes. Newtonian mechanics describes the motion of bodies in flat space and time at low speeds. Special relativity describes motion in flat space-time at speeds near light. Both are classical non-quantum theories. General relativity is also classical, but unlike the former two, it applies to curved space. It doesn't predict quantum phenomena like Hawking radiation. For that, we need quantum field theory. Like special relativity, general relativity is a principal theory, not a constructive one. General relativity's strength lies in two key principles: equivalence and general covariance. All bodies fall alike, regardless of composition. A freely falling test particle follows a geodesic, a straight path in curved spacetime. In a local freely falling system, no experiment can distinguish between a uniform gravitational field and an accelerating frame. This is the essence of the strong equivalence principle. Locally, gravity disappears and special relativity holds, but only locally. Over larger regions, tidal forces emerge. These differences in geodesic paths arise from space-time curvature. While working at the patent office, Einstein found himself daydreaming about gravity. One day, a simple but powerful thought struck him. If a man falls freely from the roof of a house, he doesn't feel his own weight. That was it, the seed of a revolution. In that fleeting moment, Einstein realized that a falling person wouldn't feel gravity at all. Everything around them, tools, papers, even their own limbs, would seem to float. It would be impossible to tell from within the fall whether gravity existed. This wasn't just a curious idea, it was a breakthrough. Einstein's insight led him to formulate the equivalence principle. Falling freely under gravity feels the same as floating in deep space. It marked the beginning of his journey toward general relativity, a theory in which gravity is not a force, but the shape of spacetime itself. Einstein illustrated the strong principle of equivalence in his 1938 book, The Evolution of Physics, co-authored with Leopold Infeld. In this book, he introduced the now famous elevator thought experiment. Imagine a large elevator suspended from the top of an immensely tall skyscraper. Suddenly, the cable snaps and the elevator begins to fall freely. Inside is a man performing experiments, unaware of the fall. In this idealized scenario where air resistance and friction are ignored, the man lets go of a handkerchief and a watch. To an outside observer, both objects fall toward the Earth at the same rate, demonstrating the equality of gravitational and inertial mass. But from the perspective of the man inside, the objects appear to float motionless, as if gravity had vanished. Since everything around him, including the elevator itself, is accelerating downward at the same rate, he experiences weightlessness. He can push objects in any direction, and they will move uniformly unless they strike the walls. No inertial experiment allows him to detect the presence of a gravitational field. This leads to a profound insight. A freely falling reference frame in a gravitational field is locally indistinguishable from an inertial frame in the absence of gravity. The effects of gravity are effectively cancelled out within the falling elevator. However, this inertial behavior is only local, bounded in space and time. Eventually, the elevator will crash or the object will collide with the walls, ending the illusion. Einstein used this thought experiment to argue that gravity is not a force, in the Newtonian sense, but rather a manifestation of spacetime geometry. This realization became the foundation of general relativity, in which gravity is described as the curvature of spacetime, and locally the laws of special relativity still apply. In 1911, Einstein realized that if acceleration and gravity are equivalent, then a light beam in an accelerating elevator should appear at a bend. Imagine an elevator being pulled upward with constant acceleration. A beam of light enters horizontally through a side window. From the perspective of an inertial observer outside the elevator, the beam of light travels in a straight line. However, during the time it takes for the light to cross the elevator itself is accelerating upward. As a result, the light strikes the opposite wall at a point lower than where it entered. To the outside observer, this is simply because the elevator moved upward while the light was in transit. The path of the light remains straight in space. Inside the elevator, the observer feels as though he is at rest in a stationary gravitational field due to the equivalence principle. He expects that a beam of light entering horizontally will travel in a straight line and hit the opposite wall at the same height. But it doesn't. It hits lower. From his perspective, this means the light must have followed a curved path downward. To explain this, he concludes that gravity must have bent the path of light. Einstein drew a profound conclusion from this thought experiment. Light bends in a gravitational field. Why? Because although light is massless, it carries energy and momentum. And in general relativity, those act as sources of gravity. According to the equivalence principle, acceleration and gravity are locally indistinguishable. So if light bends in an accelerated frame, it must also bend in a gravitational field. This thought experiment led Einstein to predict that starlight would be deflected as it passed near a massive object like the sun. That prediction was famously confirmed in 1919 by Arthur Stanley Eddington during a solar eclipse, marking one of the first major confirmations of Einstein's theory of general relativity. According to the general principle of relativity, all coordinating systems are equally valid. Laws of physics must hold in any frame. This is mathematically expressed using tensor equations, which remain valid under any coordinate transformation. This principle is reflected in general relativity's field equations and the geodesic equation. Einstein introduced the rotating disk thought experiment in 1916 to explore how motion affects the measurement of space and time. His goal was to show that geometry, once thought to be absolute, actually depends on the observer's frame of reference. This insight became a stepping stone toward general relativity. Imagine a large circle or disk. Consider two observers. One is in an inertial, non-rotating frame, standing still relative to the disk center. The other is on the rotating disk itself. Both try to measure the disk's properties, its circumference and diameter, using identical measuring rods. For the inertial observer, the rods are stationary and the geometry appears Euclidean. The circumference divided by the diameter equals pi. But for the observer on the rotating disk, the situation is different. The rods used to measure the circumference are moving relative to the center of the disk. According to special relativity, An inertial observer would see these moving rods as length contracted. Therefore, to the rotating observer, more rods are required to span the circumference than expected. Meanwhile, rods laid along the radius are oriented perpendicular to the direction of motion and are not contracted. As a result, the ratio of the circumference to the diameter are greater than pi. This reveals that the spatial geometry experienced on the rotating disk is non-Euclidean. Einstein extended the thought experiment to include time. He imagined placing two identical clocks on the disk, one at the center and one near the edge. The clock at the edge is moving faster due to the rotation, according to special relativity. As viewed from the inertial frame, it ticks more slowly than the clock at the center. This is a manifestation of kinematic time dilation. But Einstein went further. He noticed that an observer on the rotating disk experiences a centrifugal force that mimics the pull of gravity, an insight grounded in the equivalence principle. This led him to consider how clocks behave in a gravitational field. He realized that time must also pass differently in regions of different gravitational potential. Clocks deeper in a gravitational well tick more slowly than those higher up. This is known as gravitational time dilation. In the rotating disk analogy, the outer edge feels a stronger artificial gravity than the center. So even from the perspective of the rotating observer, the clock at the edge lags behind the one at the center, not just due to motion, but due to the effective gravitational potential. This insight generalizes time dilation from special relativity to general relativity, where time itself becomes a function of space-time curvature and gravitational fields. This leads to a profound conclusion. Space and time are not absolute. Their measurements depend on the observer's motion and gravitational environment. The rotating disk shows that both geometry and time behave differently in accelerated, non-inertial frames. Space becomes curved and time flows at different rates depending on position and motion. The rotating disk was a crucial conceptual bridge from special to general relativity. It showed that classical Euclidean geometry fails under acceleration and hinted that gravity too should be understood in terms of curved spacetime. It also echoes Mach's principle, which suggests that inertia is shaped by the distribution of matter and motion in the universe. In the disk experiment, geometry and time are no longer fixed. They are dynamic, responsive to acceleration and energy. In short, the rotating disk thought experiment reveals the flexible relational nature of space and time, paving the way for Einstein's general theory of relativity, in which space-time is curved by mass and energy, and the flow of time depends on both motion and gravity. John Archibald Wheeler once said, "Space-time tells matter how to move. Matter tells space-time how to curve." Einstein's field equations relate space-time curvature to energy and momentum. That is, Einstein tensor equals Einstein's gravitational constant times stress energy tensor. The Einstein tensor is built from the Ricci tensor, Ricci scalar, and the metric tensor, which describes geometry. The stress energy tensor describes matter and energy content. These tensor equations are valid in all coordinate systems. To solve them, we often seek exact solutions like the Schwarzschild metric, which describes the spacetime outside a spherical, static, non-rotating mass, a black hole. At the center of a black hole lies a singularity where spacetime curvature becomes infinite and general relativity fails. The Schwarzschild solution implies a region from which nothing can escape. The event horizon inside all paths lead to the singularity. But remarkably, there is room inside a large space-like volume. General relativity transformed our understanding of the universe. It revealed that gravity is not a force, but the manifestation of curved spacetime. From elevators to spinning disks, from equations to black holes, Einstein's vision endures. Thank you for watching this presentation.